Swayam Prabha. Digital India. Educated India.
So the previous lecture, we started off with concepts of virtual ground, and then we went through common mode rejection ratio for single-ended output as well as differential output. This lecture, we are going to start talking about the input referred offset voltage. We are going to look at where it comes from, how to calculate it, as well as one of the, as I said before, one of the main motivations in what we are doing right now is we are trying to build an op-amp, and we are looking at practical limitations of the op-amp when we design it using real world components. As you're designing the op-amp, you would like to have as high gain as possible, and we're going to look at various techniques using which we are going to increase the gain of the op-amp. Let's get back to our blackboard now. We're going to talk about non-ideality of the op-amp, DC offsets, and today we're going to learn all about them. What is DC offset? So DC offset is the input DC voltage that you need to apply at the input to make the output equal to 0. Let me explain. Input referred offset voltage, VOS. Let's say you have an amplifier, okay, plus minus, and you're supposed to get the output or multiple outputs. Then what we expect is the output to be A times V plus minus V minus. Ideally, if both V plus equal to V minus, then output V out should be equal to 0. However, because of the manufacturing variations, or there are multiple causes, you can have an offset, and that offset you can refer it at the input as VOS. The sign is not important because it could be plus or minus. If I apply equal and opposite voltage, so I can make this ideal op-amp, meaning everything is matched properly, or there is no offset inside this op-amp, and I'm bringing this offset as input referred offset, bringing it out. Then I would have to apply externally, I will have to apply this VOS to get the output 0. Okay, maybe I'll take an example to make it even clearer. So the input referred offset voltage VOS can happen because of multiple things. One is systematic offset. So this could be just by bad design, if you don't bias things properly, if you don't match your VDS. So for example, when we have a current mirror, and if you don't match the VDS, then the current will be different in the two sides. So VDS mismatched. So these are all design related problems. Okay, and the other one we don't have much control over, which is random offsets, and these are happening because of process variation, which means if you have two transistors, they will not be exactly identical. They will have differences in their properties, and due to those properties, you're not going to see, their performance is going to be different from each path, and as a result of which you will see an offset voltage. So let's draw a schematic, and with the schematic it would be a lot clearer what I'm talking about. Let's take a really simple diff pair example. This is the positive input, this is the negative input, and then this would be your positive output, and this is your negative output. So you're going to measure V out over here, let's say. Now R1, R2, M1, M2. What are the different things which could give rise to offset? Okay, first one is obvious, which is resistor mismatches, and the second one would be the transistor M1 and M2 mismatches. So you could have in the transistor, you can have W by L mismatch, which means that both the transistors are drawn with certain W by L which are exactly the same. However, when the chip is manufactured or is processed, then the W for the left side is slightly higher than the W for the right side, or something like that. Length is different. So W by L mismatch for these two transistors, M1 and M2. Also, you can have VT mismatch, VTH mismatch, and this is due to the doping and things like that. You can have mobility mismatches, oxide thickness mismatches, and things like that. So these are the multiple factors which can cause mismatches. What we can do is we can, let's say if I apply a same voltage to both sides, I short both the inputs and apply some voltage here, VDC. If there are no mismatches, then output should be exactly equal to 0, because both sides will have identical current flowing through it. The resistors are identical, the devices are identical, and when you take a difference between the two sides, then you should have 0 output voltage. Unfortunately, because of mismatches, you will see some offset coming at the output. You will have some V out 1. Then what you do is you apply an equivalent voltage in that case. How do you measure DC offset? You apply a equivalent plus minus VOS such that the output equal to 0. So this is called input referred offset. The way then to calculate would be, first of all, you connect the two inputs to the same voltage such that everything is in saturation, and you measure your V out, which is with V plus equal to V minus. You measure your V out, differential output voltage, and you divide that by the gain, differential gain, and that would give you equal to VOS input referred. So then if I apply an equal and opposite voltage of VOS, then you're kind of nulling out the output to give you V out equal to 0. So this is the definition of input referred offset voltage. So let's look at different components of offset and try to understand how do you calculate the offset. So first one would be, let's say you have VTH mismatch. I'm just going to show only this part because that's the only relevant part. So you will have two transistors. One of them will have VT1, other one will have VT2. Let's call it VTH1 and VTH2. Then it should be fairly straightforward by Kirchhoff's voltage law that I can model this as a delta VTH over here, because I'm finally applying the voltage right like this. This delta VTH is VTH1 minus VTH2 at the input. Only if the transistor mismatch is there, then VOS input referred offset will be straightforward, will be equal to VTH. What this is telling you is that if VTH1 and VTH2 are different, let's say they are different by 10 millivolts, then I can apply an input referred VOS which is equal to minus 10 millivolts. So that way you will get both the currents to be identical. Both the currents in these two branches will be identical, and it will behave as if there is no offset in these two transistors. This one is pretty straightforward, the contribution due to delta VT. Now let's look at resistor mismatches. If you have resistor mismatch, so for example, one resistor is R, the other resistor is R plus delta R, or you can also use R plus delta R divided by 2, R plus delta R, R minus delta R by 2, something like that. Okay, then you can say that due to just the resistor mismatch, my V out is going to be, V out due to resistor mismatch will be I times delta R D in this case. Okay, because we call this is the drain resistor, delta RD or delta R, whatever you would like to call it. Let's call D because for the MOSFETs we call it drain resistor, right? And for bipolar we call it RC. If there is a mismatch between the two resistors, then I'm going to get an output voltage which is differential output voltage, okay, which will be equal to I times delta RD. What would be the input referred VOS? So VOS, I'm just writing things a little bit more in detail. Input referred, and due to R mismatch. And that would be equal to, you look at the final output and you divide that by ADM, which is your differential voltage gain. So in this case it would be I times delta RD divided by, what is the differential gain? It's GM times RD. We have done this before. So then this is going to look like I divided by GM times delta RD divided by RD. Similarly, you can also, if you remember, the device if you remember the MOSFET equation, right, I equal to K divided by 2 VGS minus VT square. Right now I'm just going to assume mismatch in this entire quantity. We just looked at VTH mismatch, and you can look at K, which is mu n Cox. So K is equal to mu n Cox W by L. I'm going to group these together and look at the mismatch effect of this K, right? So you can also prove it to yourself that follow the same method, the VOS input referred due to K mismatch will be equal to, you can convince yourself that is I divided by GM, and then here you will get delta K divided by K. Whenever we use this, these are average values, because you'll have K1 and K2, and we look at the average value and we look at the differential value delta K. If you remember, K1 is equal to K average plus delta K divided by 2, K2 will be K average minus delta K by 2. So we kind of calculated offset due to input referred offset due to VTH, input referred offset due to delta R, and input referred offset due to delta K. You don't just write all three offsets and just add them together, because these are randomly varying quantities. So you have to take a mean square addition of all these randomly varying quantities, because this is a statistical effect, right? So the VOS overall is equal to VTH square plus I divided by GM, I square GM square, and then in the bracket we can do delta RD divided by RD square plus delta K divided by K square. Again, as I said, I, GM, RD, K, these are all average quantities. So this is the way you calculate the input referred offset for a MOSFET diff pair. You can do the exact same analysis for a bipolar junction BJT amplifier, and we'll go through that. So for BJT amplifier, and you will see kind of a pattern developing which will help you, kind of apply that logic every time. So in this particular case also we will apply an offset between the two.